Okay, so thank you very much. Today I'll be talking about the possibility of having instanton-solitons contributing to perturbative amplitudes in 5D Young-Mills. This is work done in collaboration with Andy Royston and is a project which is finishing and should appear soon. So let me give you some brief motivation, personal motivation behind this project. There's a recent string-motivated conjecture relating the strong coupling limit of 5D Young-Mills with maximal supersymmetry and the 2,0 theory in 6 dimensions, which is supposed to be describing the low-energy dynamics of multiple and fibrins in M theory. I don't want to say too much about the motivation behind this conjecture itself, just that a crucial role in coming up with this idea comes from the fact that 5D Young-Mills has a conserved current, J, given in terms of the Hodge dual in 5 dimensions of the second chunk class here of this of the gauge field in 5D Young-Mills. So, as such, there are states in 5D Young-Mills which actually carry instanton charge given by some integer k. And these states are crucial for comparing and matching the spectra of 5D Young-Mills and the 2,0 theory. In particular, there are some states, some finite energy stable particle configurations in 5D Young-Mills, which have as profiles the usual profiles of instantons in 4 dimensions. So they have associated moduli having to do with the position of these solitons and their size, etc., global gauge orientations. But from the point of view of the 5-dimensional theory, since these are particle solutions, they are solitons of the theory, and that's why I'll refer to them as instanton-solitons of 5D Young-Mills. I repeat that the profile of these configurations is the usual profile for instantons in 4D. So the issue, however, with this conjecture is the following. So 5D Young-Mills is a theory which has a dimensional coupling. J Young-Mills squared has dimensions of length. As a result, this is a theory which we learned very early on is non-renormalizable. So the conventional way of thinking about it is that since it's weakly coupled in the IR and strongly coupled in the UV, the theory should be thought of as a Wilsonian effective action up to some energy scale, above which you should UV complete this with some well-defined theory. Potentially with some new degrees of freedom appearing above that scale. So there was some belief initially that maybe 5D Young-Mills, because of this conjecture relating it to the 2,0 theory on a circle, might be in fact perturbatively divergent. But it was shown earlier this year by an explicit heroic calculation by these people that there exists a divergence which appears without having cancellations which come from supersymmetry at 6 loops, and that kills that idea completely. So what I would like to discuss today is how can it make sense to consider the 5D theory at strong coupling and as a result at high energies, since the 5D theory is itself not well defined. Well, in order to do that, we can contemplate the following possibility, and in fact, wonder whether the instanton-solitons, which are very important in the comparison between the spectra of the 5 and 6-dimensional theories, could actually play a role in the cancellation of these perturbative UV divergences. So this is not something that you would usually think of doing. Usually we think of solitons not contributing to perturbative amplitudes. We think that these contributions are exponentially suppressed in the gauge coupling. And in fact, that's what I would like to revisit in this talk today. So let's set up some formalism here, and which I'm going to consider for some generic theory in D dimensions with some gauge field. And then we'll see whether this formalism leads to the expected results for monopoles in 4 dimensions and how that extrapolates to instanton-solitons in 5D. So let's consider the gluon self-energy. This is the amplitude for gluon. Through the optical theorem, the analyticity of this matrix tells us that we can insert a complete set of states, intermediate states here, which I denote by this boldface F. These states can be single or multi-particle states, and as such, the sum here is over the full Fock space of the theory, and here I'm integrating over the appropriate measure of this multi-particle phase space.
This assumes there's a unitary theory.
Yes. So I'll assume that the theory is well defined, and I'll try and account in the end for the cancellation of these divergences. So naively, you'd think that the only things that could appear in these intermediate states should be perturbative particles. However, topological charge conservation tells us that there can be solitonic states, the total topological charge of which can add up to 0, which should also be considered. These states have still non-zero overlap with the incoming gluon state. This includes, as I said, soliton and soliton states above some particular energy threshold, which is equivalent to the energies of the incoming gluon being twice the soliton mass. And even though you can have a host of such multi-particle soliton-soliton states, the total topological charge of which adds up to 0, we'll consider here just a single soliton-soliton pair for simplicity. So let's see what this amplitude looks like. I denote this soliton and soliton state by P prime and P bar here. This is the soliton of momentum P prime, and then here is the anti-soliton of momentum P. And as usual, you can relate this amplitude to a matrix element involving this time-ordered product of interacting Hamiltonians for your theory. Now, we can, for a theory which involves, of course, gauge interactions through which the solitons interact with perturbative particles, the interacting Hamiltonian will involve a term here which has the gauge current multiplying this gauge potential term. So by performing a simple weak contraction, you can get rid of this A mu and this incoming gluon state here, pulling out a factor of a vector polarization vector. And you apply also crossing symmetry to take this anti-soliton to an incoming state, and you end up with a soliton form factor for this gauge current. Therefore, the pair production amplitude, which will tell us whether these soliton-soliton states could contribute to this perturbative amplitude, reduces to the valuation of this so-called soliton form factor. This is simply a one-point function in the soliton, the one soliton sector. And I'm going to be interested in the semi-classical, in the leading contribution of these soliton states. So I can look at this in the semi-classical approximation, also known as the Manton approximation. In that approximation, we can define the soliton states in terms of this integral over the moduli space of these solitons. Here, the soliton states denoted by this boldface P don't necessarily involve only the momenta associated with the translational invariance of this soliton in whichever theory you're interested in, but also could involve other discrete and continuous parameters which labels the soliton. The square root of G here is simply the volume form on the moduli space, and psi is the wave function on the soliton moduli space. So in this semi-classical approximation, the full quantum dynamics of the theory reduce to a quantum mechanics on the moduli space of these solitons. And similarly, you get that this one-point function of this soliton form factor reduces simply to the expectation value of this classical gauge current evaluated in the soliton background. So this is simply given by this expression involving the wave functions on the moduli space, and as I said, the classical gauge current evaluated in the soliton background, integrated over the d-dimensional moduli space. So this is what we need to evaluate in the various examples that we're going to be interested in, and this is what should dictate whether the soliton and soliton pairs are going to be exponentially suppressed or not, depending on the theory. So let's be a bit more specific. Let's see how that applies in the context of monopoles in four-dimensional SU2 Yang-Mills-Higgs theory, where you expect that the answer will be the conventional exponential suppression of these amplitudes. For this case, and since we're considering monopoles of topological charge 1, we expect that we only have 4 bosonic moduli. 3 of those are associated with positions of these monopoles in R3. And there's also a U1 global rotation, which has to do with electric charge. So I'm not going to be focusing on this to save some time. I'll just tell you that when you perform the integral over this U1 rotation, you just get a shift in the electric charge by 1 unit between the incoming and outgoing soliton state. The interesting physics come from the integral over the non-compact moduli. And since the moduli space for the position moduli is just R3 for a monopole in SU2 Yang-Mills-Higgs theory, what you get for the soliton form factor in the semi-classical approximation is simply the Fourier transform of the classical gauge current evaluated in the monopole background. So let me say that this expression here reproduces semi-classical results for soliton form factors in lower dimensional theories, which appear in the old literature of soliton literature of the 70s by people like Goldstone and Jakiv, Cullen and Gross, and others. So let's be even more specific and calculate this expression concretely. I'll just flash the quantities involved. The monopole solutions, the Toft monopole, Polyakov monopole solutions in the VPS limit are given in the hedgehog ansatz by Higgs field, which is a function of this function h. and the gauge potential, which involves the function k. These have some particular expression. The only thing which one needs to take into account here is that there is a g here, which is the coupling of the four-dimensional theory, and phi infinity is the asymptotic value of this Higgs field at infinity. So if you take all of this, plug it into the form for the gauge current, and evaluate this explicitly, perform the Fourier transform, you get an explicit analytic expression. I'm not going to show this expression here because it's quite complicated and not very illuminating, but the physics is hidden in what I've denoted by curly f here, which is a function of the momentum transfer, p minus p prime, and over g times phi infinity. I'm not going to show what this function looks like analytically, but I can, in fact, plot it for you. And as you can see, this function is actually exponentially suppressed at large momentum transfer, p minus p prime. So this is not very surprising. In fact, this result was to be expected. One could have predicted it from the beginning. From using the Riemann-Lebesgue lemma, the classical gauge current is a smooth function of its argument. It's also a function which has a nice fall-off at infinity. As such, it's integrable in R3. And the Riemann-Lebesgue lemma tells us that the Fourier transform of such a function, in fact, goes to 0 faster than any power as p minus p prime goes to infinity. And this is a nice argument that Tom Banks told me about in predicting the form of this form factor. So now that we have the form factor and we know that it's exponentially suppressed at large momentum transfer, the question is, how is this related to the soliton and soliton pair production, monopole and monopole in this case? Well, you can use crossing symmetry to take p prime to minus p prime again. And the four-dimensional kinematics actually tells you that this should be bounded by twice the monopole mass. And as a result, the pair production amplitude at large momentum transfer is going to go like this power here. Now, once you plug in what m is and what phi infinity is with respect to m, you recover the usual exponential suppression of minus 1 over g squared. So there is another nice way of rewriting this result in terms of this effective dimensionless parameter of the size of the soliton over its Compton wavelength. And in fact, if you try and extrapolate that to the 5-dimensional case, you immediately see that you'll get something which looks like this in the exponent, g angle squared in the denominator, but a dimension-full length scale in the numerator. And this is the size of the soliton in 5D Yang-Mills. And since you can have Yang-Mills solitons of arbitrary small size, it is plausible to expect that there's going to be contributions which give finite per production soliton amplitudes in this case. So this is the expectation. If you extrapolate this result, let's see if it works out in practice. And let's see what happens, as I said, in the case of 5-dimensional super Yang-Mills theory. Well, the two things that we need to calculate is the gauge current evaluated in the classical background and also the wave function on the moduli space of these instanton configurations. So let's start with the gauge current. The classical gauge current is given by this right-hand side. However, naively, you expect that this current is 0 in the instanton background because the instanton profile doesn't have any non-zero scalars or fermions turned on. So in fact, for pure Yang-Mills theory, you wouldn't expect to get any kind of contributions, not even exponentially suppressed for this instanton and instanton pairs. However, here we're considering a supersymmetric theory, and we have instanton solutions which have a set of bosonic moduli, but also a set of associated bosonic zero modes, but also fermionic moduli and associated fermionic zero modes. And you can turn on these fermionic zero modes, and that leads to a non-zero result for this right-hand side here. In fact, you can express this gauge current in a nice way in terms of this commutator of bosonic zero modes. These capital M and N's here run of the dimension of the moduli space. And this eta bar eta is a bilinear in these fermion collective coordinates. Of course, the form of the gauge current depends on which theory you're explicitly looking at. Okay. So the Manton approximation in this supersymmetric case leads to a reduction of the full quantum dynamics to a super quantum mechanics on the moduli space of these instantons. In fact, you can obtain the super quantum mechanics by starting with the classical Lagrangian for 5D Yang-Mills and doing the Manton approximation that reduces the dynamics to the super particle mechanics. It's a theory with 8 real supercharges. And as you can see, there's a kinetic term here for the bosonic collective coordinates, and also kinetic terms for the fermionic collective coordinates, some potential term, and the geometry of the moduli space is very explicit in the metric of the moduli space here, and also a Riemann curvature tensor for the moduli space. So in principle, we'd like to evaluate the full wave function on this moduli space. This is very difficult for generic theories. But if we concentrate on SU2 gauge theories, with, as we said, soliton number 1, you recover a nice moduli space, which is metrically C2 times C2 mod Z2. This moduli space is flat, so this potential vanishes. And what you need to do is simply quantize this free superparticle mechanics. There's a couple of ways of doing that, which in this case are equivalent. And it involves promoting the wave function to a spinor in moduli space. So you can solve for this spinor explicitly, and you get a 16-component wave function spinor, which depends on various parameters labeling that wave function. Just a couple of words about what these parameters are and what this moduli space corresponds to physically. You have a C2 here, which corresponds to the 4 translational symmetries of the instanton particle in R4. There is also a set of SU2 mod Z2 gauge orientations, global gauge transformations. Since all the fields that you've got in 5D angles are adjoint, you need to mod out by the center of the group. And there's also an instanton-soliton size, which plays the role of the radius of this S3 mod Z2 here. As such, the various quantum numbers and parameters that appear in this wave function involve the momenta associated with this C2 factor. There is also 3 SO3 quantum numbers associated with this SU2 mod Z2 factor. There is a dimensionful parameter which is continuous and is related to the size, let's say, roughly speaking, corresponds to energies corresponding to fluctuations in the size of this instanton-soliton. And there's also various discrete parameters which label the spinor.
So the space is not metric on this space, right?
Yes, it's this metric which is flat.
Does it have an ADS5 factor?
It does not. No. It does not have an ADS factor. So the measure on this thing is exactly this. So an ADS5 you'd expect some R5, I think, rho 5. I think the large n, asymptotically, if you take the SUN gauge theory at large n, that looks asymptotically like the ADS5 up to 1 Van corrections. But this is something you can calculate very explicitly. You can actually, calculate the metric just by the prescription that the metric is given in terms of the integral of the moduli space of the bosonic zero modes. Okay, so in order to evaluate the form factor that we're after, we've pinned down what these wave functions are. We've also, we are now able to evaluate the classical gauge current evaluated on the instanton background, and we need to put everything together and perform the integration of this 8-dimensional moduli space. So this is something which in practice is quite complicated, but we've done it explicitly for all cases. As you can see here, these states, each of these states is going to be labeled by 8 parameters like this. So there's lots of freedom in having an incoming state with labeled by so and so, such and such parameters, and an outgoing state labeled by other parameters, and this is just blows up the complexity of writing down the final answer. So I'm not going to write the final answer, but I'm going to tell you the main features. There is an SO3 integral which produces finite shifts in the relevant quantum numbers and doesn't affect whether these amplitudes are exponentially suppressed or not. This is very similar to what happened in the case of the monopole with the U1 integral, which led to shifts in the electric charge of the incoming state. There is an R4 integral, which leads to a Bessel-K function. On its own, this leads to exponential suppression at large momentum transfer. And this is what you would expect by the application of the Riemann-Lebesgue lemma that gave us exponential suppression for the monopole case. However, in this 5-dimensional example, you also have another integral over the size modulus. And by performing that, you end up with an analytic answer which doesn't lead to exponential suppression. Let me give you an example for a very particular choice of incoming and outgoing soliton states, where I've set all the SO3 quantum numbers to 0, and I've picked up some particular value for the discrete parameters, where I've also left free the momentum and this other parameter mu. And at large momentum transfer, k going to infinity, you see that the answer depends on some negative power of the momentum transfer and does not lead to exponential suppression. So with that, I'll start summarizing and concluding. We can evaluate these form factors for all initial and final soliton states. Even though I just gave you one example, the list is quite long but comprehensive. And as such, you can draw the conclusion that instanton-solitons in 5-dimensional maximally specific Young-Mills actually can contribute to perturbative amplitudes. This happens crucially because of the presence of a size modulus for these solitons. And I think, even though we've looked at only one particular example, which has to do with a single instanton-soliton pair produced by this perturbative gluon, it should, if you included all possible such configurations, it should affect the UV behavior of the 5D maximally specific Young-Mills theory. And the fantasy, of course, would be that if you added everything properly, you'd get a cancellation of the 6-loop perturbative divergence that Byrne, Dixon, Douglas, and friends found earlier this year. And of course, this is very reminiscent in spirit, if not in details, of the resurgence and trans series, where somehow you take a theory and combining the perturbative and the non-perturbative sector, you end up getting a well-defined theory in the end. So I think it would be very interesting to see what ideas from this topic will have to say about the above. And that's it. Thank you.
So given that these solitons are some current states of the perturbative quanta, and there an issue with the possible Talon counting of the contributions if you let them run into the loop?
Yeah, but I mean, wouldn't that be the case also for this trans series and resurgence?
No, I'm not talking about that.
Yeah.
But your scenario is that you have to let those things run into the loop to cancel the perturbative.
That's right.
Divergences.
So I think if you want to think of it like that, it might be that this is an effective way of encoding the infinite. So if you were able to actually, count an infinite number of perturbative diagrams, you'd get some similar kind of, you'd get a coherent state which wouldn't come with some exponential suppression in its factor, but would come with this finite contribution.
It's a drastic organization of the perturbative state.
That would be one way of thinking about it, yes.
Does it have to be also 5 loops or 6 loops, or you can?
Yeah. So as I said here we only looked at one gluon producing a single pair, a soliton and a soliton pair. So as such, we valued the form factor where the instanton number was 1. This crucially affects the moduli space dimension. So moduli space is 4nk for instantons, 4 times 2 times the soliton number. So for this 8-dimensional moduli space, we could explicitly solve for the wave function. If you start adding higher, and higher instanton numbers,
The right asymptotics.
which
Does it have the right asymptotics to cancel the perturbative UV divergence at certain?
well, I can't even answer that question since I have to resum all the instanton sector in order for me to.
The particular form of the expression has dependence only on some absolute values. Is that because you capped spherical symmetry? I mean, the formula has absolute values.
That's true.
Is that just artifact that you use the approximation as spherical?
That could be the case. The answer is that I haven't thought about that. I don't know if that's the case. But you're wondering about the asymptotics of the answer and what that can.
You could change the analytical structure.
Your result is not spherically symmetric because you have that explicit dependence in the right direction.
Oh, that's right. That's true.
It's just because you've chosen to look at a very particular amplitude. Yeah, it's just because he's.
No, but the question is about the dependence on the modulus of the momentum vector. Yeah. Yeah, sorry, but he's right. The solution is not spherically symmetric. There is a part of the final form factor which depends on the direction of this momentum transfer.
Can you consider that from this modular environments?
Okay, good. So that's one thing that one could think about. So one thing would be to actually, the fantasy, as I said, would be to see that there's divergent contributions coming from this instanton-soliton sector, which actually cancel exactly the divergent contributions coming from the perturbative sector. However, there could be also finite contributions from this instanton sector. And Mike was thinking about taking an amplitude, a perturbative amplitude of 5 Young mills, and put it on a circle, and then requiring S-duality invariance of that amplitude. And he found that the answer was not S-duality invariant. So the idea would be that, yes, such contributions, if they are correct, they should somehow combine with the other contributions that he was talking about to give an S-duality invariant answer. So that might be something that you wouldn't have to do at 6 loops. You could say it at a much lower loop order.
Is there any field theory where this works?
None that I know of. And I think this mechanism, in fact, doesn't depend, just depends on having a size modulus for your soliton. So that should work.
The N-4 theory in 4 dimensions could be on.
But then the instantons there are not soliton particles, right? Whereas the solitons of the theory have fixed size. They're the monopoles.
Okay. Thank you. Thanks, the speaker.